Good afternoon, all of you. My name is Dr. Deepak Yadav, and today we are going to study some another complex topic in the digital system design subject, that is ripple counters. So the counter is basically the device that counts the digit like 0, 1, 2, 3, 4 and up to the certain count, and then it repeats itself. So this is counter. So counter is basically classified into two categories, synchronous counter and asynchronous counter. So ripple counter is basically your asynchronous counter. So the verification of the counter, so the distinction of the counter is like introduction of counter, in which we study how the counter actually work, and the counter is classified into two categories, ripple counter and parallel counters. Why parallel counter? Because the clock was provided to the synchronous counters are simultaneous. So these counters are generally very fast counter in compared to asynchronous counter, where the output of the one flip flop is used as the input to the another flip flop in asynchronous counter, which is generally slow due to this category. So the counter is the circuit that cycles through the specific number of state, like it counts like 1, 2, 3, 4 and then repeat to 1, 2, 3, 4, 1, 2, 3, 4. In this way, this is a 2-bit counter that count from 0, 0, 0, 1, 1, 0 and 1, 1 and then repeat to itself. So the counter is generally the things that counts the certain number of digit. So it is classified into two categories, parallel and ripple counters. In parallel counters, for designing that counters in digital system design, we generally use flip flops. So if we have a 2-bit counter, we need 2 flip flop. So as the number of bit increases, the number of flip flop increases. As many bits are required, that much the flip flop is required for a particular counter. So for 2-bit counter in any of synchronous and asynchronous counter, we need 2 flip flop. For 3-bit counter, we need 3 flip flop, and 4-bit counter, we need 4 flip flop. So here this is the flip flop and this is the clock that is provided to the flip flop. So if the external clock is simultaneously provided to both the flip flop by a single source, then this kind of counter is called synchronous counter. So as the clock is simultaneously given to these two flip flop, the output is generated simultaneously at both the output of the flip flop. So these counters are fast, as the counter is provide the count parallelly at the output in the parallel fashion. While in the asynchronous counter, again, if we take the example of 2-bit counter, 2-bit asynchronous counter, the clock is provided only to the first flip flop and the output of the first flip flop drives the clock of the second flip flop. So a propagation delay of the gate that is used inside the inside this flip flop, the propagation delay of these gates are add up and the output is generated at this counter after the propagation delay of these flip flop. Now let us consider an example. Let's suppose 2 AND gate is used inside this counter, inside this flip flop, and the propagation delay of the first flip flop is, let's suppose, 1 millisecond and the another is again 1 millisecond. So the output is travel through 1 millisecond and then another 1 millisecond to the output, and then it comes to here, which is again takes some time to process this data. So after 2 millisecond we get the output over here. So this is in this way it takes time. The output generate at the different number of bits takes time, and which is equivalent to the propagation delay of the gate used inside the flip flop. So as the output ripples from this output to this output, from this output to the next input, so that's why it is known as the ripple or asynchronous counters. So we generally in the today's lecture we go for this asynchronous counter today, that is ripple counter. Ripple counter allows some flip flop output to be used as the source of the clock for the another flip flop. As we can see over here, the output of the first flip flop is used as the source of the another source of clock as at the another flip flop, while in synchronous counter the same clock is applied to all the flip flop, as we can see over here. Now, asynchronous counter does not change state at exactly the same time as we see in the previous slide. The output is generated after the propagation delay of the different gate inside the different flip flop. So the output is not generated simultaneously at all the bits. So it takes time. Also known as ripple counter, as the input clock ripples through the count, cumulative delay is added up, as this is again the same thing over here. Then n flip flop. N flip flop means a modulus 2 to the power n count. We need n flip flop. If we count 0 0 0 1 1 0 and 1 1, we required, if it has 2 bits like 0 and 1, we require n flip flop, that is 2 flip flop for 2 to the power n count. So 2 to the power n is equal to 4. So for the 4 count, we required 2 flip flop, that is n is equal to 2 flip flop over here for each 2 to the power n output. For the 3, we required for 2 to the power 3 count, that is 8 count, we required 3 flip flop to make this counter, and this is called the modulus of the counter. The output of the last flip flop, that is most significant bits, divide the input frequency by modes. So as we can see over here, like if we take the example of 3 bit count, one one 0 0 0 0 1 0 0 1 0 and 1 1 1. So if we take the most significant bit, for each clock pulse, each count is increasing and increasing simultaneously. So it takes 8 flip flop, 8 clock pulse to go through the count number 0 to count number 7, while the most significant bit is flip only twice. So this is also used as frequency divider circuit. It divides the frequency which is coming, the clock frequency which is coming is divided by like 2 to the power n, so that we get only 2 state change in the most significant bit. So these kind of counters are also used. This is one of the application of the counter which is used, the counter is used as the frequency divider as well. So for the ripple counter, we required either T flip flop or JK flip flop. So this is the example of JK flip flop, which is made up of AND gate. As we can see, the different AND gate is used, and this is the truth table of this flip flop, how the flip flop behave for the different number of input. So if this is the input J and K, and this is the external clock provided to this flip flop. So if clock is 0, there is no clock, whatever the value of J and K, the output is fixed as the previous position as well. QT plus 1, yani next state is equal to the previous state as well in both the output. This is output QT and this is output QT bar. So for when clock is arrived, clock is 1, and if the input is 0 0, the output is same, that is QT and QT bar only, and this is known as no change state. While when clock is 1, and the output input is 0 and 1, K is equal to 1 and J is equal to 0, the output is again QT and QT1 plus 1, again there is no change over here. And for 1 0 and for 0 1, this is known as set. This is known as reset state, as the main output, that is QT became 0 and QT bar is became 1, and this is 1 0. In this case, the output is the main output, that is QT set to 1. That's why it is known as set state. Or QT plus 1 became 0, and for 1 1, there is a state that is known as toggle, in which the output is flipped between QT bar, QT and QT bar. So as we can see, it is QT bar. In the next clock pulse it became QT, in the next clock pulse again it became QT bar. So this state, this toggle state is used in the different ripple counters to count the different counts. Like if we set the J and K permanently to 1 and only change the flip flop, the output is flip 0 1 0 1 0 1. This property is used in the different flip flop, different counter. This property of JK flip flop and T flip flop is used in the different counter to count the different number of states. So this is the example of 2-bit asynchronous up counter. Up counter means is count up like 0 0 then 0 1, then 1 0, and then 1 1. For the 3-bit counter, it became 4, 5, 6, and 7. So in this way, this is a up counter that counting in the upward direction. So here we use 2 JK flip flop, as it is a 2-bit counter. As we already study for 2 to the power n count, we require 2 to the power n count, we required n flip flop. Here for value of 4, n is equal to 2. So we require 2 flip flop over here, J and K. This is the clock pulse that is applied to this flip flop, and the output of this flip flop, as we can see, QT bar output is provided to the clock of the next input. So this is a ripple counter because the output of the first flip flop drives the next flip flop. So this is flip flop 0, this is flip flop 1, the output of the first flip flop drives the another flip flop. This is the actual clock pulse, and we set J and K of both the input as high. So J is equal to 1, K is equal to 1, here J is equal to 1, K is equal to 1. So always this state is known as toggle state. So these flip flop are always in the toggle states only. Now if we see the clock diagram over here, this is the incoming clock. As this is only a triangle over here, this means that the clock is positive edge trigger. As we can see, there is 2 edges of the clock. This is upcoming clock, yeah, positive edge, or this is negative edge, that is going down, negative edge that is going down. So we have 2 type of clock. We have 2 edges of the clock, and these flip flop are either trigger at the positive clock or the negative clock. So if we take the positive edge of the clock, the symbol is like this. If we take the negative edge for the triggering, if we take the negative edge of the clock, the symbol is having one not symbol, that is one circle over here also. But in this case, this is only triangle. That's why we take the positive edge triggering of the flip flop. So this is the clock input. This is the next. This is the clock input for the next flip flop, that is QT bar. So as the leading edge comes, the output flips. This output flips simultaneously. The opposite is generated over Q0 bar. So if this is 1, this became 0. And as again the positive edge clock of the second clock pulse arrive, it again flips to change state from 0 to 1, and again for the next it again change from 1 to 0 and then 0 to 1. In this way, the clock of the next flip flop is derived by the clock of the incoming flip flop. Now if we take the output counts, what is the output counts? Initially both the counts are 0. Q0 is 0, Q1 is 0, as we can see. As the positive edge come, this Q0 flip is state, it is a positive edge is coming, and as the positive edge is coming, the flip flop goes into the toggle state, and flip is the state, whatever the state, it changes the state, like from it is here from 0, it becomes 1. So this change to become 1, but there is no input clock to over here. So that's why this is set to 0 only. Now when the positive edge of this Q bar is coming over here, then this flip flop flip is state. So it flip is state over here, and this again flip is state as the second coming edge of this clock pulse is coming over here. So it again changes the state. So this became 1 and this became 0, and in the next this became 1 and this became 0. Again at the next stage, there is no positive edge over here, only the positive edge of this main clock is coming. So only this Q1 changes the state, Q bar set to 1 only, Q1 set to 1 only, and in this state both the positive edge of both the clock pulse is coming. So it's set to set state, both the outputs changes state to 0 and 0. So in this way the count is 0 0, 0 1, 1 0 and 1 1. So in this way, if we take the output of these counters and use as the output, so for Q0 it is 0 0 previously, then 0 1 and 1 0 and then 1 1. So in this way the ripple counter, 2-bit ripple counter work. This is the state diagram or timing diagram which shows the change in the state 00, 01, 10, 11, then again 00, 01, 10, 11. As the clock pulse is coming, it repeats the state simultaneously. That's why it is known as asynchronous counters. This is the example of 3-bit asynchronous counter in which we require three different flip-flop. As we can see over here, the actual clock is coming to this flip-flop only. Again, it is a positive edge trigger, so as there is no bubble over here. The output of this flip-flop drives then another flip-flop, then output of this flip-flop again drives the next flip-flop. So actual count is coming after the propagation of delay of these two flip-flops. So that's why these counters are relatively slow in compared to synchronous counters. So again, timing diagram is almost same. This is the first leading edge is coming where the flip-flop 1 changes its state, while this is not changes its state as it is already at 0 and at 1, and it trigger from 1 to 0, that is negative edge that is coming, which is not over here. So if we plot q0 dash, so the edge is that is going down over here. So that's why there is no flipping for this flip-flop and there is no flipping for this flip-flop. Again, when the next edge is coming, then it is trigger, it is going down, then q dash bar is going up. So the next flip-flop q1 changes its states, but this is again remains to the same value. So for the third, it again changes state, it became same, and in the fourth, it changes state, and it changes state. All the flip-flop are changing state because all the flip-flop is having positive edge over this point. So in this way the count is going increasing and increasing as the clock pulse is coming. So the actual count is 000, 001, 010, 011, 100, 101, 110 and 111, and then again reset to 000, and in this way as the clock pulse is coming, the continue counting from 0 to 7 and then again 0 to 7. This is a 4-bit ripple counter. This time negative edge triggering is used. So as we can see, there is a bubble over here at the input of the clock pulse. This means that the clock pulse is negative edge trigger. So this time when the clock pulse goes from high to low, then the triggering happens, otherwise triggering is not happen. So for this, for up counting, again for the up counting, the clock pulse is not derived by Q0 bar, it is derived by Q0 only. So the Q out, it became output as well as the clock for the next input. So output, and clock for the next flip-flop also. So for negative edge triggering, here it comes the negative edge. So as the negative edge comes, this output trigger is a state from 0 to 1. So this became 1 and all the next became 0, as it is not, the edge is not going from 1 to 0, it is going from 0 to 1. So there is no triggering in these 4 flip-flop. In these 3 flip-flop, only first flip-flop is triggered. Again for the negative edge, this negative edge is come which triggers this flip-flop. This became 1, this became 0, and this became 0, and this became 0. Again for the next, this became 1, this became 1, this became 0, and this became 0. So in this way the count is going up to 1, 1, 1 and 1, and then again reset to 0, 0, 0 and 0. So the counting is start from 0, 0, 0, 0 to 1, 1, 1, 1, and then again reset to 0, 0, 0, 0. It is a 4-bit counter, as we need 4 flip-flop to trigger this. So this is the up counter. If we want to design a down counter, like as we can see over here, for the negative edge triggering, again over here, negative edge triggering, if we provide the edge clock to the next flip-flop by the Q bar dash, Q bar B, then the counting is start negative as the edges changes. So the count is start from 1, 1, 1, 1, 1, 1, then 1, 1, 0, then 1, 0, 1, then 1 0 0, then 0 1 1, 0 1 0, 0 0 1 and 0 0 0, and then again reset to 1 1 1. So as just by changing the output terminal, we can convert the from up counter to the down counter using asynchronous counter. So if we want to drive the counter in the both state, in the up as well as down, we need a mode select circuit over here. In mode select input, if we set the input to like to 0, this 0 is connected to this gate, this became 0, this became 0, so that is no clock pulse is coming from here, and due to this 1 it became 1, due to this NOT gate it became 1, and this terminal became 1, and this terminal became 1. So whatever is coming at this, it is going out to this. So for the up counting, when m is equal to 0, when m is equal to 0, for the up counting, this gate works, and these gates not work. So the clock is provided by the QA terminal, QB terminal to the next flip flop, and the count is that is increasing count, that is up counting in this way. While if it is set to 1, then this gate and this gate stop working, and these two gates are start working. As due to this NOT gate, this 1 became 0, this is not working now because this is connected to this and this is connected to this, while this one is working when this is connected to one terminal. So these two gates are working, which behave as a clock to the next flip flop, and the count for m is equal to 1, the count start from 1 1 1 to 1 1 0 to 0 0 0. So with the help of this mode select circuit or mode select input, we can trigger this same counter as the up counter as well as the down counter, as we can see over here. Now modulus 5 counter. So in some application of the ripple counter, we not required the counter goes from to the maximum state, like from 0 0 0 to 1 1 1. If in some cases it required, it counts only up to the mode 5. So this is the design of the counter with the help of ripple counter, which count up to the mode 5. So for this we made a truth table. These are the state of the counter from 0 to 8, from 1 to 8. These are the count 0 0 0 to 1 1 1, and this is the output that is required at the output for our count, that is for valid states, and these 3 states are non-valid state and it is not required in mode 5 counter. So mode 5 is count up to the state 5. So the output became 1, and rest of the state which is not used, we have the output became 0. So if we make the K map for this output for the counter state QC and QB and QA, as we can see over here, this logic is generated as this: Y is equal to QC plus QB, QB bar and QB bar and QA bar, QB bar and QA bar. This is something cutting over here. So this is QC plus QB bar, QA bar over here. So by using this this output, we reset the circuit as it crosses the state number 5 to state number 6. It reset to state 0 0. How this is work? There is one terminal known as clear terminal in each flip flop. So as we provide the 1 over this clear flip flop, whatever the state of the flip flop, it simultaneously reset the flip flop to 0 0 0 state. So if with the help of this circuit or at the output and with the help of output count, we provide this circuit to the output count, and the output of this circuit is provided to the reset input of all the flip flop. So according to this logic, as the state 5 passes and states the counter is try to come into the state 6, it reset the flip flop to again state 0 0 0. It became reset to 0 0 0 and again start counting. So in this way, mode 5 counter only count from state 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 1 0 0 and 1 0 1, and then again reset to 0 0 0. So this is the mode 5 counter in which only 5 states are counting by the counter over here. Next is asynchronous counter for a given sequence, like in some application the counter is required in such a way that it not only count from 0 to 5 but it count from 6, 7, 6, 5, 4, 3 and then reset to 7. Then for these kinds of this kind of design, again we do the same method, in which we take the count of the flip flop and write down all the state and put 1 for each valid state which is required and 0 for invalid state, which is 1, 2 and 3 over here. Again make the K map, and with the help of this K map provide one signal to the clear input for those state which is not required, that is 0, 1, 2 and 3. For this logic, create 1 for these 3 state which clear the flip flop to 0, 0, 0 and the flip flop count only 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0 and 0, 1, 1 and again reset to 1, 1, 1 state. So this is 7, 6, 5, 4, 3 and this is again 7, 6, 5, 4, 3. So in this way asynchronous counter can be designed for any number of count from different number of state, different number of switching, as we can see over here. So thank you. This is all for the today's lecture. This is basically on the ripple counters. In the next lecture we probably see the how the synchronous counter works. Thank you for